So this is a picture of the core of Virgo cluster. This is a so-called Markarian chain of galaxies. It's only like 15 to 20 megaparsecs away from us. And so clusters are certainly the... there's a little bit of a editing problem there. Clusters are very prominent parts of the large-scale structure, right? And they've been the first one to be seen. And only a small fraction of all galaxies are in clusters. Most of them are in groups. But interesting things happen in clusters of galaxies. So how did it look like? This is Virgo cluster, the closest one to us, center of the local supercluster. The picture on the left is X-ray image. You can see the individual bright galaxies superposed on an overall cluster X-ray emission. On the right is map of where optical galaxies are. So it kind of follows the same structure. There's of the order of a couple thousand galaxies. Almost all of them are dwarfs. Only a few tens are really big galaxies. So Virgo is not a very interesting cluster. It's a very poor cluster as clusters go. Coma cluster is more like a real thing, and that's 100 megaparsecs away. And here again you see X-ray and optical pictures, and they're a superposition. And this turns out to be fairly typical of what clusters might look like. There are very prominent X-ray sources, and that's important in finding them. And another important nearby one is called Perseus cluster. This is somewhere in between Virgo and Coma in terms of overall mass and density. The brightest galaxy there, NGC 1265, is actually housing one of those obscured quasars in it. And if it wasn't for obscuration, maybe even visible by naked eye, but fortunately or unfortunately, it is obscured. And so the same thing carries on as you keep pushing out in redshift. The galaxies become harder and harder to see, but X-ray gas is easily detectable. There is very little else that can be confused with. I mean, they're quasars, but they're all point sources as opposed to clusters, which are kind of well-resolved blobs of gas. And even the most distant clusters that we now know, which are now of the order like 2/3 of the look-back time to the Big Bang, are following similar kind of behavior. So, having a problem with the PowerPoint on this laptop. So there are several ways in which clusters can be found. In the optical, we can look just for overdensity of galaxies. Sometimes we can use colors to look for elliptical galaxies. But then you're vulnerable to superposition of structure of different redshifts. In X-rays, it's much easier because it's very distinctive. There is very little confusion, and that's by far the best way now to find clusters. A new method is so-called Sinaev-Zeldovich effect. I'll explain that in a moment. And also you can use gravitational distortions or gravitational lensing to look for those. That's very hard to do. There are several important trends that you see. And one is that clusters range from very symmetric, well-relaxed looking that are elliptical galaxy rich to very loose, fluffy, irregular ones that are mostly spiral galaxy rich. And the former are more luminous X-ray sources. So it's all understood in terms of clusters just coming together and galaxies plowing through the X-ray gas. Spiral galaxy disks would lose their gas and become S0s, eventually merge as ellipticals. And so we see clusters in different dynamical stages of formation. The most relaxed ones, the ones full of elliptical galaxies, are the oldest. And those which are irregular, still full of spiral galaxies, are the youngest. You may remember that free-fall timescale is a few billion years for a cluster, and so you expect clusters to be still forming. So the X-ray gas is interesting, and it's millions or tens of millions of degrees. Some of it came out of galaxies through stellar winds, supernova winds. They're pushed out. Some of it is just pristine gas that came in from the universe that was never in galaxies. We know that some of it was in galaxies because it's not pure hydrogen and helium. Its metallicity is about 1/3 solar, so that is likely to come out of elliptical galaxies. And X-ray luminosity correlates with all other important properties, masses, and what have you. It also has substructure, and some of it is due to clumps of galaxy groups falling in. Some of it is due to active nuclei, those jets, disturbing the gas. So they're not perfect, uniform X-ray sources, but they contain interesting signatures of past history. I mentioned Sinaev-Zeldovich effect, and this is what this is. Here's a cluster, it's a blob of X-ray gas, hot gas, electrons. And behind it is cosmic microwave background. So those low-energy photons from microwave background come through this hot gas and do inverse Compton scattering on those fast electrons, which boosts their energies at the expense of the energy of electrons. And so now cosmic microwave background looks a little hotter right against the cluster. Not due to the temperature of cluster, due to this energy exchange process. And at the bottom you see the radio map of one of those clusters that show a bump in microwaves that corresponds to the same distribution of X-rays. Now, since you're not looking at source itself, source is the microwave background, this is redshift independent. Source is always in the same redshift. So this effect, unlike everything else, does not depend on distance. Right? So you can find clusters using this technique very, very far away. And now this is a very popular way of finding clusters for cosmological purposes with Planck satellites and others. We talked already about dark matter in clusters, and just to refresh your memory, the idea here is that these X-ray particles, those test particles in gravitational potential, if it's in virial equilibrium, temperature is related to kinetic energy, you go through the numbers, you find out that clusters have hundreds of times more mass that can be accounted by the visible material. And this has been actually demonstrated very clearly with gravitational lensing signal. They can map amounts of mass due to the lensing of the background galaxies, and what's shown here, so-called bullet cluster, where blue blobs are the dark matter distribution inferred from lensing, pure gravity. Red stuff is hot X-ray gas superposed in an optical picture. So what happens is you have two clusters, they collide, dark matter clouds kind of go through each other because they're collisionless, but gas collides, gas stays. So you have now dark matter has passed out, and the gas remains in the middle. Eventually, those two blobs of dark matter will come back and things will settle into virial equilibrium. But you're encountering this merger of two clusters right after the first passage. Several other cases of this have been found now. And that's seen as one of the important pieces of evidence that indeed the reason why we think there is dark matter there is correct, because it's confirmed by this gravitational lensing as well as this dynamical process. Mentioned that spiral galaxies, as they fall into these X-ray atmospheres of clusters, will get stripped away of their hydrogen, and therefore star formation in them will be depressed. So evolution of galaxies will be strongly dependent on where they live. Spirals in dense cluster environments will get snuffed out very quickly, and those in field, like Milky Way, say, will just keep making stars at uniform pace. A very nice illustration of this is a combination of radio maps in neutral hydrogen of spiral galaxies in Virgo cluster. The center is M87 galaxy in Virgo cluster, central Virgo cluster. You can see that spiral galaxies are smaller, closer to the middle, and bigger on the outskirts. And that's exactly what you expect. Those on the outskirts haven't really been stripped yet. Those that fell through only have the innermost parts left. And the same kind of thing then is seen in so-called intracluster light. As galaxies pass by, distort each other, there are these tidal tails, the below splatter of stars all over it, and there will be sort of diffuse light of stars that now belong to the cluster, not to every galaxy, that sort of accumulated as a result of all these galaxy interactions. And in order to see them, you have to look at very, very low surface brightness level. So people who have done that did this for the Virgo cluster, and the missing holes are where the bright objects are. But you can see that there are galaxies, but have kind of very extended envelopes. There are also some of those kind of tidal tails and features, all of which are due to the past dynamical interactions. So stars now belong to the cluster potential more than they belong to the host galaxies themselves.